Hello, my name is Nigara Romi, and in Lab 4 we are discussing oscillations. The goals in this lab are to predict the motion of oscillation of a spring mass and compare it to the experimental data. We want to examine the modeled energy changes during the oscillation of the spring, understand how the different forms of energy present in a system influence the other energies. Our findings point out that the motion predicted for the x direction was similar but slightly greater, and in the y direction was much less in the experimental data. When it comes to energy, the total energy is 0, which proves a point later on in the video. There are two main fundamental physics principles at hand, the first one being Newton's second law, where we use F net and momentum and the velocity update formula. And the other principle would be the energy principle, where change of energy equals work done by the surroundings plus thermal energy. And there are also different forms of energy present in the system, three of them being a kinetic translational, spring potential, and gravitational potential. But other forms of energy exist, such as thermal and rotational kinetic. When looking at the system, we have the spring, mass, and earth. And in static equilibrium, there are two main forces acting on the mass, which would be force of the spring bringing the mass upwards and force of gravity bringing the mass downwards. Since the surroundings are nothing, the work done by surroundings is 0, so change in energy is 0. When looking at the tracker to get our experimental data, these are our specs for the video, as well as the mass of the object and the initial variables that we got from the data, which were then put into the glow script code. The spring constant and relaxed length of the spring were also given in the pre-lecture video, but here are the equations that show how we derived those two values. We also found L hat, and S using the physics principles that we know, and we also added in the kinetic, gravitational potential, spring potential energies, and updated those later on through the iteration. And again, the two forces present are force of gravity and force of the spring, which make up our F nets. And again, we iterated the process by putting in Newton's second law of position and velocity update formula. And we also iterated the energies present in the system as well. And here is our graph for our results. We see that the energies, which we have delta K, delta UG, delta US, those all zero out, and the orange shows that the total energy is in fact 0, and total change in energy is in fact 0, and the position on the right, we have the X on the top and Y on the bottom. The X is very similar, the model is very similar to the experimental, with the model being a little bit greater, and in the Y position, the experimental is greater in value than the model, but this could be due to issues when tracking data. Maybe I didn't put the marker in an accurate location, or I didn't account for other forms of energy such as thermal, rotational kinetic energy, or energy that escaped through sound. And the energies cancel each other out, resulting in 0 change in energy. Now, what does it mean? Is the energy principle satisfied? Well, since the total energy was 0 all throughout the model, the energy principle was in fact satisfied. The spring potential energy is always opposite to the gravitational potential energy, and the kinetic energy has the same sign as gravitational potential energy, but has less magnitude, resulting in a net 0 energy. Now, what if the oscillation periods of the X and Y position were different? Well, they actually are a little bit different, with a difference of 0.068 in the difference of periods, and this can result differences in calculations of spring constant K, spring force, and relaxed length of the spring, but it could also be caused by drag force or incorrect tracking of the center of mass. Thank you.